Welcome to Statistics in Excel number 80. Hey, if you want to download this workbook and follow along, click on my YouTube channel and click on my college website link, and you can download the workbook Business 210 Chapter 8. Hey, we're in Chapter 8 here. We're going to talk about confidence intervals. And we're going to use Z and T. Well, we know how to use Z. We're going to learn a new distribution, the T distribution. And then we'll see how to calculate or determine sample size. Now, let's just remember where we came from. We were just in Chapter 7. Now we're going on to 8. What do we do in Chapter 7? We knew some or assumed information about the population mean or standard deviation sigma. And then we made a reasonable statement about x bar. We came to conclusions like, we are 95% sure that our x bar, our sample mean, will occur between two values. So some lower and some upper values. In this case, it was 95% probability between those values. And we said that, yes, our sample mean should occur between those. But what are we going to do in Chapter 8? We don't have information about the population mean, or in some cases, the population standard deviation sigma. So what are we going to do? We're going to take a sample and get an x bar, add some room for error on either side, right? Because if we're taking an x bar, there's almost always sampling error, because x bar doesn't always equal mu. So when we have our x bar, since we want to use it to estimate the population parameter mu, we have to add some error on both sides. And then we're going to make a statement about mu. Here's the kind of statement we want to make. We are 95% sure that the population mean, mu, occurs between this value and this value. So this is much different than what we were doing last chapter. Take a sample, add some room on either side for error. That's called our confidence interval. And then make a statement about the population mu. This is very powerful because then people can make claims about what the average is. And then we can go test them with a sample. Now, point estimates. We've talked a lot about this already. We know that our x bar is the point estimate for our mu. Population proportion point estimate for our population, or sorry, sample proportion is an estimate for our population proportion. And our S, that's our sample standard deviation, is a point estimate for sigma, population standard deviation. Now, point estimate for mu is x bar. That's what we're going to use. But why do we need to use sample mean x bar anyway to estimate our population mu? Remember, these are all averages. Why do we need the sample? Because most of the time we just don't have the population mean. For example, we do not know how many meals married couples eat out each week. There's no place to go get that number. So we could take a sample, our x bar, and get some margin of error on either side. And that will be the point estimate for our unknown population mean. Now, we can't just say x bar is population mean. That's where our confidence interval will come in. Another example, we don't know what the mean amount of profit per auto sold in the USA is. But we can go take a sample, and our x bar will be the point estimate. Again, x bar is not going to be exactly equal to. So in this chapter, we'll add some margin of error on either side, build a confidence interval, and then we'll be 95% sure that our population mean will be between two values, all based on an x bar. Now, what if x bar as the point estimate for our population mean? What about that sample error? That's what I was just talking about, because they're not always equal. X bar does not always equal mu. So we can't just use x bar. We're going to have to add some error below and above to x bar to get a range of values that we can use to estimate our mu, population mean. That's where confidence intervals come in. A definition for confidence intervals: a range of values constructed from sample data. Notice constructed from sample data. So we're not going to know anything about that population mu. But a range of values constructed from sample data so that the population parameter mu or p, our population proportion, is likely to occur within a range at a specified probability, usually like 95% or 90% or 99%. The specified probability will be called level of confidence. Now, sometimes it's called level of confidence. Sometimes it's called confidence level. Sometimes it's called confidence coefficient. It's all over the place. Even this textbook we're using here, which is pretty good, they call it officially at the beginning confidence interval, but then some of the homework problems all say the confidence level is 90%. So those are all synonyms. Here's an example and we're going to do this one just in a moment. For building a deck on a house, we are 90% sure, this is for a particular company, right, that the population mean lies between 8 hours, 47 minutes and 7 hours, 13 minutes. Now, that is officially, that 90% will be our confidence interval, right? And we'll have these two values, and then we'll say, well, the population parameter lies between those. But what about the other 10%? The level of confidence is 90%. There is a 10% risk that the population mean is not in our confidence interval. We'll also use the words confidence limit. So the upper and lower limit for our confidence interval, they're called confidence limits. Now, confidence level, sometimes you'll see it as that. Sometimes you'll see it as confidence coefficient, like I mentioned before. There it is, 0.9 as a proportion, or 90% as a percentage. This will give us how likely the population parameter, how likely the population parameter will occur in a range of values. So that's like the definition of what confidence interval will give us. Level of significance. This is that risk I just mentioned a moment ago. It's often called alpha. When we get to next chapter, we're doing hypothesis testing. We will no longer mention confidence level or level of significance so much. We'll use alpha. Alpha is always 1 minus the confidence level, right? So if we're 90% sure that our population parameter happens in an interval, then 1 minus that will give us 0.10 or 10%. This is the risk that the population parameter is not in our interval. It is the risk that we take, in making a mistake with our inferences. Now, I'm going to skip through here. Here's the formula we're going to be using. These are my handwritten notes. We'll go over to Excel. But there's our x bar, right? Plus or minus. There's our z. We'll also see t here. And there's the standard error. As we saw last chapter, you cannot just use sigma, if you know it, or s for sample standard deviation. Because when we're plotting x bars, those are all averages. So as we saw last chapter, our distribution of sample means is much smaller, much less dispersion or variation. So that was the number we use called standard error. That's the standard deviation of our sampling distribution of sample means. So in essence, that's our standard deviations, right? And as we know, z is number of standard deviations. So if we have a 1 here, 1 times the standard deviation. 2 times the standard deviation. Oh, yeah, that's the amount above or below our x bar that we're going to add and subtract to get our confidence interval. Now, here's a bunch of notes here. I even have there's a bunch of different methods we can use in Excel. Here's some handwritten notes. Let's go do this in Excel. So here's our example. Solid construction company constructs decks for residential homes. They send out 2-person teams to build decks. The company conducts a sample of 40 jobs and calculates a mean completion time of 8 hours to build a typical deck. The standard deviation for the population is known and is equal to 3 hours. Now, a lot of times this isn't known, and there's some good detail in the book and in my handwritten notes. Most of the time, you have to estimate it. Sometimes, for example, you might have to do a pilot study to calculate it beforehand, or maybe it's known, in this case, from population data. Nevertheless, I'm actually going to do this same problem once where we know it. And that's not unlikely for a company to know their standard deviation for the population. But we're going to do it once where we know it. And then I'm going to show you what happens if we don't know it. And we'll have to use the t-distribution. And our interval will be much bigger, right? Here we know it. And we're going to use it in our calculations. So that reduces some of the spread in the data. But if we have to use a sample standard deviation, we're not quite as sure. So we have to make a bigger interval. All right, you ready? So here's some of the data. Our mean is 8. 8 hours to build a typical deck. Our n, that was our sample size. Sigma, I don't need those 2 decimals there, do I? Because sample size is a whole number, 1, 2, 3, 4, 5, etc. Oh, and sigma, population standard deviation, that is known. Now, this is S, or our standard error, not sigma. This is going to be in hours. All right. So here we calculated. We did this a lot last chapter. Equals, we take our known population standard deviation and divide by the square root of our n. Right? That makes it much smaller. So it was 3 for the population. Now for our sampling distribution of sample means, much smaller our standard deviation. All right, our level of confidence. This is how sure that our pop mean is in our interval. That's 0.9. Now, our level of significance equals 1 minus. This is the risk we're willing to take that the pop mean is not in the interval. Now, we're going to use alpha divided by 2 in a bunch of different situations. So I'm just going to calculate it right off the bat. Divided by 2. Hey, why would we have to? If this is our risk, you know, if you have, in fact, I'll just show you a picture of it right now. There it is. Our confidence interval is going to be there. We're going to have 7.2 hours and 8.8, right? Oh, that's the 90%. Well, everything under the curve, our sampling distribution of sample means equals 1. So if this is 90, there's some up here and some down here. Next chapter, we'll call this a two-tail test. So that's why if it's 10%, this would be 5, this would be 5. That is what that alpha divided by 2 means. In the textbook, they always talk about it up here. So alpha divided by 2 is the area right there, and they're always calculating z right there. I'm going to show you a couple different ways to do it. Calculate z here or here. And we did that. We actually have all the tools from last chapter to already do this. We know how to do this particular one. All right, now here's the first way we can do this. I want to calculate a z on the lower end and a z on the upper end. Now, we know if we have probability from last chapter how to calculate the z. Now, the z on the lower end will be easy. If we're looking at our picture right here, we got to remember all of these functions go cumulatively from here. So we need to do one norm S inverse with 5%, and then one norm inverse from here all the way to there. But wait a second. What's the probability from there all the way back to negative infinity? Well, that's where alpha divided by 2 on the upper end comes in. So if we take 1 minus alpha divided by 2, that'll give us all the area from there. And for us, that'll give us our z right there. So our z for the lower end, that's relatively straightforward. Norm S inverse. And all it wants is probability. Remember, on the low end, boom, it calculates our z. Now let's do it on the upper end. What is it here? As we just saw a second ago in the picture, it's 1 minus this. And I should have our formulas over here for you too, if you're using this as a reference later. OK, now our margin of error. And I'm going to show you 2 different ways to do it. Maybe even I'll show you 2 different ways to do it. Margin of error. Remember, that is our, we have a sample mean of 8, so we need to subtract some on the low end, subtract some on the upper end. Well, let's go ahead and calculate our margin of error. We're going to use equals. Oh, yeah, it's always just our z on the upper end. Remember, if you're calculating a confidence interval, if you have one, you have the other. You just do the negation of it. That times our standard deviation for the sampling distribution, which is our that is not S right there. I have to change that again. How about that? That's standard error. I called that S earlier. It is not. That is our standard error. I had it listed correctly here, but not over there. OK, so there we have our margin of error. There's from the number of standard deviations times our standard deviation for the sampling distribution. And boom, we add and subtract this from our 8 hours. So what do we do for the low end? Equals our 8 minus our margin of error. That's what that x bar plus or minus the margin of error means. And for the upper end, we take our 8 and we add our margin of error. So 8.22 or 8.78. Now, it really comes out to be 7 hours, 13 minutes, 8 hours, 47 minutes. And I would actually like to show you how to calculate that. I'm going to insert a new sheet. In 2007, you can right-click, insert, and then point to worksheet. There's also a keyboard shortcut. I don't think it shows you there. It is Shift F11, Shift F11. And I'm going to immediately double click that and type time calculation, just calc. How about that? And I'm going to show you another trick. We're going to come over here, and I want to actually copy these and link them over here. There's lots of ways to do this, but watch this. Copy. I'm going to come over here, and I'm going to right-click, paste special, and we have a link, paste link. Now that copies the link, but watch this. Right-click, paste special, and I'm going to paint, select formats, or formats right here, and click OK. And watch this. Right-click, paste special, and column widths. I know that's a big hassle. By the way, Excel 2010, I just got a preview of it last week. They will have a solution for exactly that, where you don't have to right-click paste special 2 or 3 times. You can just do it all in one swoop, and there'll be a great keyboard shortcut for that. But look at this. Now it's linked. Now, how do we calculate? Well, I want to insert a row up here. Right-click, insert. And I want to find the hours. Actually, I'm going to call this whole number, and then decimal. Now I'm going to highlight both cells, and I'm going to use the integer. Integer always will take the integer part. That 0.22 will go away, and it will just show the 7. Integer always goes down, so it goes from 7.22 down to 7. Close parentheses, and I'll Control Enter. So we have the hours. Now what about the decimals? Can we just say whatever this one is minus the integer, and that gives us the decimal. Oops, I forgot to hit Control Enter and populate both of those cells. So all we did was to subtract those two. And now, how do we calculate the minutes? We take, this is a decimal part of an hour. So to calculate the minutes, you say equals this. And how many minutes are there in 1 hour? This is a decimal part of 1 hour. Well, if there's 60 minutes in 1 hour, you multiply by 60. Now, what if you wanted the actual round these to the nearest minute? We're going to use the round function. Equals round. Round, it needs a number, and then comma, number of decimals. Now, the way this works is I always remember that 2 is to the penny. So 2 is to the penny, and 0 is to the integer. For income taxes, you would round to the 0. For sampling size, where you're, or in some other situations when you're going to the ones positions or integer, you put a 0 here. For us, we want to round to the nearest integer, which is a minute, so we'll put 0. And so we have a 13 and a 47. So we have 7 hours, 13 minutes, 8 hours, 47 minutes. Now we don't need those decimals there either. All right, so that's just how we calculate that. And sometimes that's important when you're doing sample stuff like this, when you do your final answer. Now I want to show you a second way to do this. And it involves the confidence function. Now what the confidence function does is it actually calculates margin of error. So we'll actually skip over the step of calculating z. Now, this method here is great because we'll have to use it when we get to proportions. So if you want to do just one method that works for the x bars and the proportions, that's it. This one, however, is faster than this method. So let's see how to do this. Confidence. And it has 3 inputs, alpha, and alpha is the whole amount, not alpha divided by 2, comma. The standard deviation, that is from the population, comma, and then the sample size. Notice it needs the raw inputs. It calculates everything it needs, including standard error. So really, we get to skip over calculating that one and our z. So this is a very convenient function. If you're using x bars all the time and not proportions, boom, this is the one to use. So there it is. Now we can calculate our, just as we did here, our 2 values equals whatever the 8 hours. And since we want 8 hours as the middle point, and we want to subtract that margin of error, and then we'll go up and now we'll get our 8 hours and now add the margin of error. See how we're adding something above and below. And that gives us our room to account for sampling error on either side. Now, what does this really mean? Here's the conclusions we can make from it. The limits for the 90% confidence interval are 7.22 and 8.78. You can say it is reasonable to assume that the population mean for hours to build a typical deck is within our interval given a 10% risk. Another way to say this is we are 90% sure that the population is between these limits. However, we do take a 10% risk that the population mean is not within our interval. So really, it's all about whether it's in the interval or not. Now, if you want to be sure, what do? You got to increase that confidence interval so you reduce the risk. Now, here's another way to say it. You wouldn't really want to say this when you're making a report, but technically, this is what's going on in statistics. If our population distribution is normally distributed and our n is large enough, remember, the larger the sample size, the better the results are going to be. If we were to construct 100 similar intervals, we would expect to find our population mean in 90 of them, and 10 would not contain the population mean. Now I want to go over to our PDFs and look at a picture of this, because this is kind of the hardcore stats of it that really tells you the meaning of it. Okay, this is page 10 of 24. And here's our 90%. Our 90% goes from right there to right there. And there is, remember, this is the sampling distribution for sample means. Mu equals mu sub x bar, or as this textbook uses, expected x bar. Those are all equal right down the middle. So watch this. Remember, we said technically when you do 90% confidence interval, you're saying the population mu is lying somewhere in between whatever interval we construct. But look at this. Here's the original distribution, but here's what we're doing. We're taking a sample and then adding some slop on either end called margin of error. Well, here's one. And did this particular one where we calculated some value, maybe we got 7.7 hours this time. So we built our 8.2 here. So we built our confidence interval. See how it spans all the way to there and there? Well, there is the mark for population parameter mu. Is it in this one? Yeah. What about this one down here? Yeah, so this one came out to be like our sample x bar was 7.7, right? So look, here's our confidence interval. Did it get it this time? Right. But what about this one? And these are only 3 of 100 you could build. But look at number 3. So we got something way out here, like the average time from our sample was close to 9 hours or something. Way out here. So when we added our slop on either end, did it get the 8? See, the 8 is would be right here for our particular example. It's not in that interval. So that's what the idea of confidence intervals are all about. So obviously 90%, if you wanted to be more sure, you'd move up to 95. And actually, most of the examples in our textbook are 90. I put a 90 in here because sometimes people use that, and mostly the book does 95, and occasionally a 99 or a 90. All right, let's go back over to Excel. And there's our picture of it right here. There's our, if I can make this a little bit smaller here. There's our picture. Confidence interval, I put all the stats right there so you could see it. But that little area there is the confidence interval. That's the risk that we are taking. Now, this is where sigma, standard deviation of the population, is known. When we come back in our next example, I'm going to show you another sigma known example from raw data, like an example you'd get in the ruler, and then we'll move on to the t-distribution when we don't have sigma. All right, see you next video.